Okay, let's look at additive notation and modular arithmetic in this section. Really, it's more of the modular, technically, like most of the problems we're going to look at right now is just complex number involved, but let's just at least look first at one thing, additive notation was for each of the following sets, tell whether it is or is not a group under addition. If it is not a group, name a group axiom it does not satisfy. So all the integral multiples of 7 is the first set, and that is, or you can just say 7z like I'll refer to it. That's basically what it is. For all intents and purposes, it's 7 times the number, is what all the integral multiples are of all the integers. Z is all integers, 0, 1, 2 to infinity, negative, or negative 1, negative 2. It's like from negative infinity to the positive infinity is basically the integers. That's what Z is. You'd have 21, 28, negative 28, you have everything. And this one is going to turn out to be a group, which I think is somewhat obvious because of its, the multiple, all the integral multiples I think will probably, but you have to always double check it to make sure. But closure is relatively, like in one of the earlier sections we did closure under addition to some extent, similar to that. We can show it. xy is in 7z, and that means that x plus y is in 7z if it does exist, and we can show it. It is yes, and we can quickly show it. So x and y are in 7z means that x equals 7a and y equals 7b, with a and b integers. And then that means x plus y equals 7a plus 7b, and then x plus y equals 7 times a plus b. So distribute, you can pull out. And that's in 7z because that's 7 times a plus b, and a plus b is an integer. So that's 7 times an integer. So it's in 7z. Identity is obvious. It even shows it, like this is given by the problem 0. 0 isn't 7z, that's all you need for additive when you add stuff for a group. Inverse, if x is in 7z, is negative x in 7z, and this is true, yes. And this is very obvious. Again, you have negative 7 and 7 being shown, and you can do that for any of the multiples. There's the negative and the positive. Associativity, x plus y plus z equals x plus y plus z, and that's for any x, y, z is in z in this format. So so it is a group under addition. It's all 4 properties, all 4 axioms, I guess is how this problem explains it. But yeah, remember the inverse, like the identity is 0 because 0 plus any number will equal the same as the original number. Like 0 plus 7 is 7, 0 plus 14 is 14. That's why in general that's true. 0 is the identity. You need 0 to exist, because no other number will fit that role. And when you add, and x is in 7z, negative x is in 7z, that's because the inverse follows that rule, because an inverse, you can recall it, like if you really want to recall, the inverse is what gives you the, when it's well, it's multiplication, it's multiply. When you add the inverse, though, to the number, you'll get identity, which in this case is a negative number to the original. Associativity is just associativity like that. A general old school math thing. Ignore this. This whole area, ignore that. So in B, it's all the polynomials ax squared plus bx plus c with a, b, and c real numbers, and a does not equal 0. Check the axioms like I show here. That s equal ax squared plus bx plus c such that a, b, c is in the domain of real numbers and a does not equal 0. That's how you'd write it out. You can just write it out like that. So you just check for everything to be in z in s. Here, find it. That's basically what it's asking. That's how I define the set. And we can just skip closure. I think it would work, but I've read that it doesn't exactly. But either way, what matters is you just need one of these to fail. So the more obvious one is the identity. 0 is in S, cannot happen. It does not. 0 is not included in S. There is no identity in S due to a does not equal 0, implying that 0 cannot equal ax squared plus bx plus c, because you always have at least ax squared basically. A cannot equal 0, so we're in that situation. If identity is not satisfied, and this set is not a group under addition. You can ignore the closure thing because apparently it seems that a does not equal 0 does not allow closure. I'm not sure about the exacts on that, but I think identity is easier to show, at least, that it does not. All the polynomials ax cubed plus bx squared plus cx plus d with a, b, c, and d any real numbers, this one's gonna work. That one's not a group, but this one will be. Because there's no other condition as part of it, a big part. Just s equals ax cubed plus bx squared plus cx plus d, such that a, b, c, d is in the real number domain. And it works, but we'll see that. So p1x and p2x is in S. So we have the two polynomials, and then is p1x plus p2x in S. And this definitely is true because you add them up. And I made a1, b1, c1, d1 for polynomial 1, and polynomial 2 was 2 subscripts. And in the process you can see I group them together, and you get, the constant, a1 and a2 added together times x cubed in the end. And you get the same form of the same polynomial, basically. So it would be an S, this polynomial. And therefore closure is satisfied. The identity 0 is an S, that's true. And you can kind of quickly check it by thinking of all these being equal to 0s, then ax cubed plus bx squared plus cx plus d will equal 0 then. So this 0 is included. Inverse. If p of x is in S is negative p of x in S, and that's true, you can think of it as I try to show really briefly, you can also have the negative, which is, so it's all these being negative. You can have a negative value for a, b, c, d. Which would be like if these were all, you probably could just say, but it works out. Associativity, of course, just the same thing, it'll work. So the set of all polynomials with a, b, c, d, any real numbers is a group under addition, as said. This polynomial type. The cubic polynomials, third degree or whatever you want to call it, is a group. So express each of the following complex numbers in the polar form. R cosine t, r times cosine t plus I sine t. So negative 6 plus 6i is the first one. You take the modulus like before, which is just negative 6 squared plus 6 squared, square root of that. You get square root of 72, and you can simplify that down. You can say 6 times 6 times 2 in it, and then 6 times square root of 2. Under the square root. And you have this as the denominator, and this is your numerators for cosine and sine. Sine is in a plus bi is b on the numerator, cosine has a on it. And we can see it's where sine is positive, cosine is negative, and that's the second quadrant, so it's 90 degrees to 180 degrees is what t can be in. Just a quick note, it should be less than or equal to, even though it's very obvious when it should be 2 is greater than 90 degrees and less than 180 degrees. And I usually just put the less than, I think, because it's an extra step, but it's less than or equal to. So t can be 90 degrees and it can be 180 degrees or anything between that. So 90 degrees to 180 is the possible thing. T is greater than or equal to 90 degrees, but less than or equal to 180 degrees. So, or you can just, it's also second quadrant. I like to think of it. So I take the inverse of one of these. So inverse cosine of 1 over the negative 1 over square root 2 is 175 degrees, which you can also convert to radians, which you need. Or you can just know it in your head what it is in radians, but I just have to show it a few times. And you come out with 3 pi fourths. And that's for both of them. So z equals 6 square root of 2 times cosine 3 pi fourths plus I sine 3 pi fourths is the answer. 9i, it's pretty quick. It's just the square root of 9 squared, which is equal to 9 for your modulus. Sine t is 9 over 9. Cosine t is 0 over 9, so it's 1 and 0. And those are exact things, so that might be wide in, but Yeah, because it'd be obvious, like whenever sine is something or cosine. Like whenever you have them in exact values like that, it's pretty obvious, but sine inverse of 1 only exists at one point, and that's pi halves, so t equals pi halves. Right, when it's equal to 1, sine of pi halves is the only one that works, so it's the 9 times cosine pi halves plus I times sine pi halves is the polar form of just 9i. And in C, it's like -5 equals -5 plus 0i. And we can tell just from that Z equals -5, A equals -5, and B equals 0. But if you want to take the modulus, you just get -5 squared, which is 25, and then the square root of that is 5, as shown here. And cosine t is -1, sine t is 0. Inverse cosine -1 only occurs at pi, so t equals pi. So z equals 5 times cosine pi plus I sine pi. That whole thing times 5, basically, is how it's been. That's the polar form. Now we want to convert each of the following complex numbers from polar form into the rectangular form a plus bi. So we have two numbers here, a and b, like we have two. So just a times cosine pi eighths plus I sine pi sixth plus I sine pi sixth. In this case, you convert from pi sixth to, you can do it to degrees you really want to if you don't fully understand pi sixth is, which I did here just to make it for the viewer. So cosine 30 degrees, sine 30 degrees. We take each of them and we get square root of 3 over 2 and 1/2 respectively. So z equals 8 times square root of 3 over 2 plus I times 1/2, which is equal to 4 square root of 3 plus 4i. And that's your form. 4 square root of 3 plus 4i. That's a plus bi format. Then square root of 2 times cosine 5 pi fourths plus I sine 5 pi fourths is a second one, and that's in polar form. So we have to convert this to rectangular form. And do it again, the conversion, 225 degrees, really want to. And it's cosine and sine of 225 degrees are both -1 over square root of 2. So z equals square root of 2 times -1 divided by square root of 2 plus I times -1 over square root of 2, which is equal to -1 because square root of 2's cancel in the denominator, multiplied by it. -1 minus I. That's it. And finally, this is the one where we use that, where we can raise it to powers. Express square root of 3 plus I to the nth power times 2 minus 2 square root of 3i. That should be 9th power in a plus bi form by first converting, and all that, you can read it. So I just say z1 and z2. z1 is going to be square root of 3 plus I, and we convert this to polar form before we do anything. I did these step by step, basically. I made them so that we'd have a very simple thing to multiply and end, basically. So z1 is equal to square root of 3 plus I, and that means r1. I label it r1 that can fit. And t1, try to be consistent here. So it's square root of 3 squared plus 1 squared, square root of that, and that's square root of 4, which equals 2. So we cosine t is square root of 3 divided by 2, and sine t is 1 over 2. They're both positive, so that means it's the first quadrant, or 0 is less than or equal to t1, less than or equal to 90 degrees. Should be less than or equal to when I write it out like that. Even though we know that with these values it won't be exactly equal to, just by looking at them, because there's specific value you should look for that, but regardless, it's that quadrant. Actually, don't worry about it. Yeah, I think less than works as well. It works. Just ignore it. I just write it however the notes your professor had it. Like, write it however the professor wrote it. If he wrote it like less than, then that's fine. When he does an example, too. What matters most is, though, you understand how to get the value t1 equals pi 6 from this. Yeah, I kind of skipped the step here, but because it's a long one already, this one. But inverse sine of 1/2 or cosine inverse the square root of 3/2 in that quadrant, first quadrant, would give you t1 equals pi sixth. So z1 equals 2 times cosine pi sixth plus I times sine pi sixth. Then you can raise this to the 10th power. So we have it in polar form. That's 2 to the 10th times cosine 10 pi sixth plus I sine 10 pi sixth. Simplify that down. You get 5 pi thirds is your t value for when it's raised to 10 power. And you don't have to do any more complicated. Then we just solve here to get z to the 10th power, z1 to the 10th power in simpler form. And this is basically my square root of 3 plus 1 to the 10th power we're figuring out. That's what z1 to the 10th is. And you work the magic here. You can multiply 2/10 into what cosine and sine are equal to. So it becomes 2 to the 10th divided by 2 minus 2 to the 10th times square root of 3 divided by 2. Just becomes 2 to the 9th minus 2 to the 9th square root of 3i, because I is right here as well. Then we do z2. 2 minus 2 square root of 3i. R2 is, you can solve to get 4, because 2 squared plus negative 2 squared is 3 squared equals 4 plus 12 in the underneath square root, so it's square root of 16 equals 4. That's the modulus. Then finally z2 equals, so we write that just to make sure, keep up to date. R2 equals 4 and z2 equals 2 minus 2 square root of 3i. Cosine d2 is either 1/2 or negative square root of 3, 2 when you simplify them down. It's the fourth quadrant because sine is negative, cosine positive. And inverse cosine of 1/2 is equal to 5 pi thirds, which is equal to t2 in this case. So t2 is 5 pi thirds. Through this method. Then z2 equals 4 times cosine of 5 pi thirds plus I times sine of 5 pi thirds. Then you raise it to the 9th power and you multiply it. You have 4 to the 9th times. You have the 9 times 5 pi thirds, 9 times 5 pi thirds like last time. Similar to last time. And 4 to the 9th is really 2 to the 18th, because that's 2 raised to the 18th power is 4 to the 9th, because really you can write that as 2 squared to the 9th, which means that's 2 to the 18th. Yeah. You know, I cancel out some terms. I cancel out, I divide 3 from each of these to get 15 pi, and 15 pi for the t value here when it's raised to 9th power. And that's equal to 2 to the 18th times cosine of 14 pi plus I sine 40 pi plus pi. You can divide out multiples of 2 pi, so that's 14 pi. And get rid of it. So it's cosine pi plus I sine pi in the thing you're multiplying by, this area. And eventually, so z2 to the 9th is equal to 2 to the 18th times negative 1 plus 0i. Sine pi is 0, cosine pi is negative 1. So it just becomes negative 2 to the 18th, which can easily, we multiply these guys together, z1 to the 10th times z2 to the 9th. It's equal to 2 to the 9th minus 2 to the 9th square root of 3i times negative 218 power. So it's negative 2 to the 27th, because you add 9 and 18, and you multiply exponents, meaning the same base. But it's negative, of course, because of that. And it's plus 2 to the 27th, because negative is saying square root of 3i. Yep, but that's your final answer. In A plus BI format, just you don't have to do an you do so negative 2 to the 27th is A. 2 to the plus 2 to the 27th power times square root of 3 is B, and I is of course I. For A plus BI. A plus BI. And that's it for that long one. Long-winded problem.